Hi there, you're in the lab with your mate JJ. So today is Maxitronix Electronics Project Day. Today we're going to keep on keeping on with our Maxitronix Sensor Robot 20, which we affectionately call our 20in1. There's 20 projects in this kit. I've done 11 of them. Today we'll be doing the 12th one. So I'm glad to finally be doing an electronics project. It's been nothing but unboxings and demos and mail calls around here for the tail end of the year. So I thought it'd be good to get a couple of actual electronics projects done before it hits 2025. So today we'll do this, project number 12, which is the Magnetism Detector. I'll show you the instructions on the computer here. After we've gone through that, we'll pop over to the booth and we'll assemble the kit, and then once that's done, we'll bring it over to the bench and we'll have a look at it with the oscilloscope, with the thermal cam, and just see what we can see about our magnetism detector. So yes, that's what this video is going to be. There should be a bunch of videos coming out soon. I actually do still have quite a number of mail call videos and unboxing videos and demo videos to do on John's Home Shopping Network. But today we're actually doing an electronics project, which is the meat and potatoes of this show. We're supposed to be doing as many electronics projects as we can. I do love the Maxitronix kits, so that's going to be a good one for today. The other thing that I'll be doing soon is catching up with my J-Car and silicon chip mini projects. Those are queued. There's a lot of them there now. They've been very busy over there at Silicon Chip releasing all those, so I've got to catch up with them. But I can only catch up one video at a time. So let's do our Maxitronix kit. And if you're interested in the J-Car mini projects that will be coming out soon, don't forget to hit subscribe. So let's jump over to the computer and have a look at the instructions for this guy. Here on the computer. So these are the instructions for this kit. This is project number 12, Magnetism Detector. What it does. Again, you use the reed switch. This time, you use the switch to detect the presence of a magnetic field. After you finish the wiring, turn on the control. The LED is light. Place magnet A near the right side of the reed switch with the white side of the magnet close to the switch. The LED goes off. Now bring magnet B near the left side of the switch, again with the white side of the magnet close to the switch. Refer to the illustrations. Okay, so we're putting the magnets on the sides there as it's shown in the figure 1 and figure 2. Both LEDs light. However, if you turn magnet B halfway round, the LEDs go off. Using this circuit, you can check to see if a piece of metal is a magnet or not. Use magnet A as described above, but call your unknown piece of metal magnet B. See if the LEDs behave in the same manner. How it works. When magnet A is positioned as shown in figure 1, the lines of magnetic force flow counterclockwise. Therefore, the right reed inside the switch is magnetized. It becomes the south pole of the magnet. The opposite side is designated as the north pole of the magnet. The right side of the left reed is also magnetized as the south magnetic pole, with its opposite side becoming the north pole of the magnet. The poles are now north and south on each half of the reed switch. They attract and the switch closes. If you bring both magnets A and B into position, as shown in the second illustration, the right reed is magnetized into south and north poles, as you look at it from right to left, but the left reed is magnetized into the south and north poles from left to right. Therefore, the center parts are both north poles. They repel each other. Opposite poles, a north and a south pole, attract, and like poles, two north or two south poles, repel. The switch is off. When you reverse magnet B, the center polarity of one reed changes to a south pole. The reeds attract, close the switch, and light the LEDs. This simple arrangement requires only one switch circuit transistor. If the switch turns on, the voltage between the emitter of Q4 stays at 0 volts. The LEDs remain off. If the reed switch closes, current flows from the base to the emitter and the LEDs light. So as you can see, the wiring sequence for this particular diagram is pretty trivial. It's only one line of, not even a full line of things. So we've got two LEDs joined with 1K resistors, and there's a 10K resistor over here as well. And we've got a switch for on and off for the circuit, and the 9-volt battery, and one of our NPN bipolar junction transistors. Now, and here is the reed switch. So we've got our two magnets, A and B. We'll have a look at that when we're over on the bench. So the first thing to do for this project is wire up this schematic on the board. So let's pop over to the booth and we'll do that together. Here we are in the booth. So the first job will be to take out the wires from the previous project, and then once that's done, we can assemble this new project. Alright, well that's done. I just left that little white wire up the back there because that's for the battery to the power switch, which is pretty much always required. So I just left that on. Now let's wire up our project. Okay, so that wiring's done. That was a real easy job, only a couple of wires. So let's take this over to the bench and have a look at it. Here on the bench. So I've got this set up just angled just right so that the glare doesn't come through on the thing. I'll show you what the problem is. Do you see how the glare comes just there? That's problematic. So I just pop this in there to try and get rid of some of that glare. Now these are our magnets. So we'll just start. Well, first of all, let's turn the project on. So that's this one. Okay, that should be on now. Now let's see what happens if we put a magnet near the reed switch. We're expecting to see the LEDs go on. I think the obvious problem here is power. I suspect there's no power in here. Let's have a look at that together. Yes, look at that. No battery. Shall we put the battery in? Why not? We could also power it off the mains power. Why don't we use the mains power? Because then we'll be able to tell how much current it's drawing, which won't be very much. It's only powering a couple of LEDs. Might even be negligible. Anyway, let's throw Ryden 1 on there, and we're going to need some alligator clips. These look like alligator clips to me. So there's a positive lead, and we're going to have a negative lead. And I suppose I can flip you over to show you Um, give me a sec, I'll just play with my cameras and I'll be back. Alright, so let me throw you over to the other camera here. There we go. So you can see the RD6006-1, that's my Ryden power supply. You can see I've got the red LED, sorry, the red lead and the black lead. So they're my leads. It's set here at 9 volts, which is correct. That was a 9-volt battery that we're replacing. And it's set to maximum current at 1 amp, so it shouldn't go above that. Over voltage at 10 volts, over current at 2 amps. So if we press on off, that should turn the power on. Very good. So we'll just turn it off and let's hook up our battery. So we've got I'll throw you back over to the bench. Here we are. So we're just connecting our battery here. We've got negative there, and I'll just turn it off, and positive here. Alright, so now we've got power, so maybe our circuit will be a bit more exciting when it's powered. Let's hit on off. On we go. Now we're not seeing anything on those LEDs yet because the reed switch isn't engaged. So let's take one of our magnets and try and trigger the reed switch. Ah, I've got to turn it on as well. There we go. On. And the reed switches are okay, so this is a normally closed switch by the looks of it, and the magnet alright, so it's just as it said. Now I'm not sure which side is north and which side is south, but if we put them like this, the lights go off, and if we turn one of them around, the lights go on, and if we turn another one around, the lights go off again. And that's everything there is to know about the reed switch. You can see that its normal state is closed, which means that current can flow, and so you would expect, oh yeah, okay, even one magnet will be enough to control the thing. So it must have a little bit of a magnetic charge itself. So that's pretty reliable there, isn't it? You turn it around, it turns itself off. You turn it around again, it turns itself on. Now, when we're here, we're drawing 13 milliamps. 13 milliamps when it's on, and when it's off, why has that? Oh, I need to turn it off by this. There we go, it's off. And now it's drawing 0 amps. Absolutely no power, or at least, yeah, okay. So, yeah, 0 amps being drawn, and it looks like 13 milliamps to power the LEDs. Cool. Well, I'll tell you what, I'll throw you over to the thermal cam. I'm not expecting to see anything particularly interesting, but give me a second. Alright, so I've got the Uni-T thermal cam, the UTI 260B, all set up there. It's on the right hand side of your screen. You can see it. The various bits and pieces that you can see are the 2 transistors you see down the bottom left hand corner there and there. Those 2 points are the transistors warming up as they allow current to pass. And of course, transistor, the name is from transfer resistor, and it's sort of like a valve, and when it conducts electricity, it does so by providing a resistance. Yeah, best thought of as a valve, not a pump. A valve, not a pump. So we can see the transistors are chewing up a bit of juice, and less so you can see at the back here, there, those 2 points, those are the LEDs. So you can see the 2 little LEDs there. It seems that the transistors are getting warmer than the LEDs, and that is, it looks like a little bit of heat being chewed up by the control switch, which is honestly a bit odd. I don't know why that would be getting warm, but it does seem to be a little bit warm. It could also just be residue heat from my fingers when I touched it earlier, because that you can actually, like, if I press here with my hot hand and move my finger away, you can see that hot dot is still on the board, and that will last there as for quite some time. And I guess the other thing we could do is we'll just disengage the reed switch. I'll switch this around. There we go. All right, so now everything's turned off. But as you can see, the thermal properties of the transistors, they are coming down. Look at that, 32.7. So you should see that 33.3. Up the top left on the thermal can, you get a reading of the maximum temperature. And when I move my body well out of the scene, you can see there's an ambient heat coming in from the side. And then you can see those transistors still showing some warmth, even though they're not powered anymore. I wonder if we turn this around, will we see that ramp up a bit? Turn that around. Are they a bit brighter now? I'm not sure. Possibly. Anyway, the one on the right seems just a little bit hotter. Oh, it's actually got the hottest point, 30.5 degrees on that transistor. And if we take it offline again, then that 30.5, it's not the hottest point anymore. Fair enough. Anyway, let's throw you back over to the bench proper. So what have we seen? There's no oscillator. There's nothing oscillating here, so we won't have a look at it under the scope. This is all just basic DC stuff. So we learned that the magnet sensor is normally closed, which means that it conducts electricity, and you can use 1 or 2 magnets to affect the switch, and that will break the circuit, which will turn it off. So it's ordinarily off. We saw the 13 milliamps for powering the transistors and the LEDs, 0 milliamps when it's off. So I just wanted to do a couple more experiments. As you can see, we can turn the LEDs off with the magnets, but it did say to try using just another piece of metal to see if that has any effect, and it doesn't. So we can conclude that this sharpener is not magnetic. But we've got another piece of metal here. This is a screw. I think it probably is magnetic. So let's put that there and see. There we go. So it is magnetized, and it affects the behavior of the circuit. Even by itself it does. Cool. Now the other thing that we wanted to just show, that you see the normally on state of this circuit is facilitated by this transistor here. What I want to show you is the continuity on the reed switch independent of the transistor. So what we'll do is we'll just well, first of all, we'll disconnect the power. I'm just going to turn the power off, and we can leave that off as well. And we're going to, let's just, for remembering, we'll just put the wires here, so we can put them back again later if we care to. Now what I'm going to do is break out my old trusty multimeter. Can you see that? I think you can. What about if I angle it up there? Can you see that? I think we're going to be beeping anyway. We're going to put it in continuity mode. So this is continuity mode. And if I toggle through the modes a bit, that's continuity mode. Now if we put the things together, can you hear that? That's a beep, beep, beep. And it gives 0.3 ohms. So what we're going to do is hook this up. I wonder if I could just put that in there, probably. So you can see we've connected the read sensor to the continuity tester, and the read sensor is in fact normally open. And if we use a magnet on the read switch, we can actually close the circuit. So yes, I wanted to show you that the behavior of the read switch itself is normally open, but when we hook it up with this transistor, the circuit functions as normally closed. So I hope you understood that difference, and that's why we use the transistor at all. We could have it the other way around without needing a transistor in the circuit. We could just literally use the switch as a switch. So yes, I hope that's clear. Now I'm going to send you over to the farewell cam, and we'll wrap up. That's a wrap. So yes, that concludes Project 12 of the Maxitronix Sensor Robot 20. That was a bit of fun investigating the behavior of a read switch. I didn't know those properties. I thought that it was a normally open system, and that you used the magnetism to close it. So I was a bit surprised to learn, but of course it makes sense, because usually you use them on doors and windows and stuff, and they're usually the door is shut, so the read is activated. So you want that to be the low power state. Anyway, it was good fun to break out our two little magnets and play with our read switch. I angled this thing on that little wedge that you can see at the bottom there, just to help with the glare, and that actually worked well. That was a nice hack. That's good. I had a bunch of them actually. I got these small little ones. You see those, and then there's this one, which is a great big honking one. The big honking one right in the middle seems to be the best. So I'll keep that handy for future Maxitronix videos. But that includes today's video. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.